Hello, everyone. My name is Ben Abbott, and I am a solutions engineer from VMRay. Today, I will speaking to you all on the ways in which ransomware evades detection. To introduce the problem, ransomware is a type of malware which encrypts the user's system and displays a ransom note for the user to pay a fee in order to release the files. Recently, we have seen an addition to this where data is also exfiltrated and the malicious actor also puts a deadline for the payment, or they will release the data. See Kenneth Copeland for a recent example. From the Verizon data breach report, we can see that ransomware is the third most common malware variety in breaches and the second most common variety for incidents. Loaders, which are used in a variety of malware campaigns, including ransomware campaigns, are the fourth most common incident variety. Malware can be delivered in a variety of ways, but what we can see from the top vectors in breaches, email links and attachments are two of the top ways which malware is distributed. Download by malware even takes a larger percentage of the breach vectors than email attachments. Protecting against phishing and downloaders are some of the most important steps for an organization to take when defending against malware. So today I'm going to speak to you about how mature organizations currently protect against malware, why malware sandboxes are a necessary component to aid these tools, and how links and attachments are handled by most email security solutions. And then lastly, we're going to talk about how malware defends against these detection methods. To fully protect the organization, you cannot focus your attention in one area of security, but you have to protect against a broad variety of attack vectors. Simply, we use antivirus and host IDS IPS, now generally combined as an EDR solution, on our endpoints. We use firewalls, web filters, and network IDS and IPS to protect the internal network and data. And we use email filters and gateways to protect users from unwanted and malicious emails. These methods are strong at detecting against known illegitimate traffic, known malware, and malicious heuristics, but they cannot detect threats that are unknown. We're seeing more malware using legitimate websites and hosting sites for distribution. Malware that has unknown hashes and heuristics can bypass even sophisticated email and web filters, as well as EDR tools. And malware is increasingly using obfuscation to bypass these controls as well. And encrypted files cannot be analyzed by these tools. This is why a sandboxing solution is necessary, because a sandbox fully detonates a sample and looks at the behavior of the submitted samples in order to determine its severity. There are many ways modern sandboxes can integrate with other IT tools, which allow these tools to submit files to be analyzed, and also have the sandbox pass the results of the analysis to those tools to aid with incident response and threat hunting. The basic process of a sandbox starts with spinning up an image to work as your analysis environment. After this, you detonate a file inside and monitor its behavior. And from this, you're able to determine if that file is malicious or not. The top way we see malware being distributed is through email links. In addition to hosting credential harvesting sites, many of these links will redirect to a host, which will push malware downloaded to a user machine. For most email security technologies, they analyze the samples at a time of click instead of a time of delivery, and present the user with a page similar to this while they analyze the link. For time of click analysis, only a reputation check is done on the embedded link before rewriting to a safe link and passing the email to a user. The URL is not analyzed further unless the user clicks on the link. When that happens, the user waits while the URL is analyzed by the sandboxing technology to determine if that link contains malicious content. The reason most email security solutions use time of click instead of time of delivery is to prioritize resources, since fully analyzing every link would take up a significant amount of product time and processing power. The drawbacks of time to click are that detection is later in the process, which increases the risk to the user as a negative impact on productivity. These can also easily be bypassed by malware authors, and the use of safe links makes it harder for other products to work together. Lastly, we see gaps in coverage, especially with attachments that have embedded links. With VMRay's Email Threat Defender, links and attachments are extracted and detonated when the email is received. and the malicious emails are moved to the user's junk folder. With VMRay, all email links and attachments go through a specific detonation and triaging process. First, they're sent for a reputation check, which can identify near instantaneously if that sample is already known to be clean or malicious. Smart caching is also enabled to stop any repeat analyses. Next, the unknown samples go through static analysis, which does a deep inspection of the documents for macros, embedded links, and documents, as well as metadata extraction for YARA and AV detection. This is completed in just a couple of seconds. If the severity of the sample remains unknown, the next stage is the dynamic analysis. Here, the sample is detonated fully in a target environment, and the behavior is then analyzed to determine if the sample is malicious. This is where VMRay separates itself with faster and more accurate results than typical sandboxing solutions. For the security and IR teams, all of this can easily be viewed in a single pane of glass view using the ETD manager, where you can quickly see any email that was flagged as malicious and what in the email was found to be malicious, and see the sender and recipient. And for a big picture view, you can use the dashboard to see a timeline of the submissions, the latest incidents, and the users who are the top targets. So with ETD, we see both faster and a wider range of detection. Not only do we support links and documents, we also see an increase in productivity. This integrates easily with multiple security vendors. And as we'll discuss in the next section of the presentation, this is also evasion resistant. Now, although ransomware is the third highest malware variety for incidents, ransomware actually only accounted for 3.5% of the unique malware samples. This is understandable considering the widespread of ransomware as a service that we've seen over the past couple of years. Because of this, a majority of ransomware samples are not trying to evade sandboxes, as the sample is most likely already known. What we're seeing more of in many malware campaigns, including ransomware, is the use of loaders. Loaders are a common way to get ransomware on the network, and they make up 19% of malware samples. At a basic level, all a loader is doing is downloading malware from a temporary file sharing site, such as Dropbox, SharePoint, Google Drive, and it uses these because this traffic is likely allowed on most networks, so it can bypass as legitimate traffic. Loaders on their own aren't actually malicious either. In fact, some like GoLoader were built with honest intent. Before loaders download and execute the malware, they use advanced techniques to either ensure that it's not executed in a sandbox and tries to hamper a possible analysis. So our threat research team at VMRay has identified a collection of sandbox evasion techniques used by malware, and these techniques can be grouped into three basic categories: detecting the sandbox, defeating the sandbox monitor and the underlying technology, and also evade the sandbox by being context aware. So first, we're going to take a deeper dive into the first technique, which is detecting the sandbox. In simple terms, malware authors want to detect if it is running in a sandbox and then have the malware act like a normal benign file. And since sandboxes run in virtualized environments, an easy thing for the malware to check is to see if it's running in a virtualized environment. So malware can check to see the registry, the processes, device names, MAC addresses, IO ports, to determine if it's running on bare metal or inside a VM. This method is less effective nowadays, as sandboxes are much better at masking that it's in a virtualized environment. And plus, as you're aware, there's a trend to run virtualization in production. So this method can limit the malware's exposure, which will limit the malware from executing on what might otherwise be valid victim machines. Another trick malware can use is to check to see if it's running in an unrealistic environment for a normal day-to-day user. One thing malware can do is check for specific vendors such as Sandboxy, which is a well-known sandbox, and Wine, which is a well-known emulator, and both of these have very specific fingerprints. Malware can also check for a realistic environment by looking for USB drives or connected printers, mail clients, and for modern sandboxes to prevent these, they need to use images with realistic resources and usage. So making sure that there is network traffic history. And so now we're going to look at GoLoader and the ways that it attempts to evade sandboxes. Bootloader is not actually malware, but a downloader and used as a means to deliver malware. It's been quite active in the past couple of months, and so far we've seen Bootloader used to deliver Formbook, Nanocore, LokiBot, and Remcos. The payload of these is encrypted and hosted on popular cloud services such as Google Drive, OneDrive, and Dropbox. The main functionality of Bootloader is implemented as shellcode, which is obfuscated and does not strictly allow function calling conventions. This is to avoid static detection and analysis. Bootloader also uses several techniques to detect the sandbox. It tries to detect an artificial environment by using artifacts of virtual machine guest agents. If any of those artifacts are found, you'll see an error message like this showing that it cannot run. These artifacts are embedded as hash values in the shellcode, and during its runtime, it iterates through the virtual memory, calculates hash values, and checks if it's found a match. If that's the case, the error message is shown and the process terminates. In addition to the artifacts present in virtual memory, Bootloader also checks the presence of the quick emulator guest agent by testing if one of the files exists. And besides the usage of artifacts, Bootloader also examines the number of top-level windows on the screen. If this number is below a given threshold of 12, it assumes an artificial environment and stops its execution. And now we're going to talk about the second approach, which is defeating the sandbox monitor itself. And this can include hooking evasion, delaying the sample's execution, and exploiting the cost of monitoring. And for many sandboxes, the way in which they monitor the behavior in the target environment is by using an agent. And this leverages a method called hooking. Issue with using an agent inside the target environment is that you're using additional artifacts which can be detected and therefore evaded by the malware. This is why an agentless approach is the best solution. By removing the agent from the target environment, the malware can be executed in a machine that has no additional sandbox artifacts that can be detected. Other more generic ways malware can avoid detection is to delay its execution. So wait for specific actions to occur, as well looking for a reboot or a login. Or it can also blind the ecosystem by using multiple compression layers or large file sizes. And now we're going to go back to Bootloader for the different techniques it uses to defeat sandboxes. A common feature of sandboxes is to monitor file system changes introduced by the analyzed software. So an analysis typically includes created and modified files. Bootloader avoids its payload to be extracted by relying on virtual memory, and this means that neither the encrypted nor the decrypted parts are into the file system. Another feature of sandboxes is the ability to dump memory regions, and because memory regions can be huge in size, sandboxes introduce limits to keep performance. Bootloader takes advantage of the limit and uses large memory regions for the shellcode and payload, which reduces the performance as they have to be processed and dumped by the sandbox. Sandboxes that are utilizing API hooking aim for the lowest possible API level, and typically they rely on user space hooking, targeting functions in ntdll.dll. Bootloader tries to undo the redirection by restoring the original code. So in effect, Bootloader is removing the hooks to avoid being monitored. For VMs, instructions can cause a transition between the guest machine and hypervisor, which delays execution. And malware can measure the resulting overhead to detect if it's inside a virtual machine. One solution is for sandboxes to put a patch the result functions and the instructions used for the measurement. And Bootloader uses this information against sandboxes by comparing the lower 32-bit values of two successive reads timestamp instructions around CPU ID. If the ID is less or equal to 0, the function starts at its beginning. So for sandboxes that patch the timestamp counter to provide a specific value, this results in an infinite loop. Now we're going to go to the third approach for sandbox evasion, which is by using context awareness. Context awareness isn't trying to detect or defeat the sandbox, but ensure that the malware will only run under specific circumstances. This can make it harder for public sandboxes to detect, as they are generally built to cater to a large but not specific set of users. One way where context awareness is seen is by requiring user interaction. And the clearest, most well-known example of user interaction requirement is CAPTCHA, which you see almost everywhere online. And malware uses features like this against us, as known that almost all sandboxes will be automated. So it's capable of checking for things like mouse movements and clicking through installers or scrolling through documents, or even clicking on embedded objects within the documents. We've even seen malware that's sophisticated enough to make sure that mouse movements aren't too fast and jitter the way a mouse would in a human's hand. Malware can also check for specific settings before fully detonating. Malware can make specific environmental queries to check the date, time zone, username, keyboard language, and more based around the result, determine if the results match the expected environment. It can also check to see if specific applications are running on the system, especially if an attacker knows a user runs a specific program, which normally wouldn't be on a sandbox. Or it can password protect files so that a human would be required to input the password, as a sandbox would not know the password. With ETD, if the attachment is password protected, ETD is able to extract the password from the body of the email, so the sample can be analyzed without requiring the user to input that themselves. So in conclusion, the best way for organizations to improve their defense against ransomware is to ensure that it is detected early and through a wide range of vectors. The detected method should also be resistant to evasion from malware. And ideally, it's also going to complement everything that we have existing already. Thank you all for attending our presentation. And for more information, please visit our website at vmray.com.